this slide shows speed up that can be achieved by multiprocessors and multi-cores. And Amdahl's law states that the actual speed up is limited by the serial fraction of programs. So even if you have infinite number of processors, if your program has some inherently serial fraction, then you cannot speed up that much. That's what Amdahl's law states. Okay? Let's look at the speed up that can be achieved by capital N number of processors. Okay? The speed up is defined by time to run a program on a single processor divided by time to run on N processors. Okay? So by having N multiprocessors, how much you can speed up. And here F is a parallel fraction of program, and 1 minus F is a serial fraction of the program. Okay? So this portion you cannot parallelize, even if you have many number of processors. So if you assume the program takes 1 on a single processor, on N processors, 1 minus F, because this is inherently serial, you cannot parallelize. Okay? So that remains the same as before. Only this fraction F, parallel portion, can be parallelized by N processors. So the speed up is 1 divided by 1 minus F plus F divided by N. And if you draw this graph, this shows serial fraction 1 minus F. If the serial fraction is about 10%, the speed up you can achieve is limited by only about 4.7 instead of 8, even though you are using 8 processors. Okay? So if you increase this serial fraction, then your speed up will be lower and lower, even if you have large number of processors. So if I give you a serial fraction of 25% with maybe 100 processors, you can compute the speed up, right? Okay, so as an example, compute the speed up with serial portion. 1 minus F is 20%, and if you have 100 processors, capital N is 100. Compute the actual speed up dictated by this Amdahl's law. Right now. Okay? Everybody. Using the equation. Do the calculation.
4.807.
Okay. So 1 divided by 1 minus F is 0.2 plus F is how much? 0.8 divided by 100. This is 0.008. So 0.2081. So this is around 4.8.
Yeah.
So even if you increase the number of processors from 8 to 100, the speed up on 800 processors is only 4.8. So almost saturation after right? 8. So serial fraction does limit the parallelism. Okay, that's what Amdahl's law states. Okay, but this is theoretical speed up. Even though Amdahl states that serial fraction limits your parallelization, in actual system, actual parallelization, actual speed up is much lower, because in real system there are always overhead. If you implement some parallel application on multi-cores, the thread or process on each core needs to communicate sometimes to do some cooperation for to do some work. And also, if you want to use multi-core or multi-processors, somehow scheduler has to distribute the workloads to different processors or different cores. The workload distribution also has some overhead. And also, each processor core has its own private cache. And shared memory multiprocessor, multi-cores, they share the memory, the second level cache, so they have to maintain cache coherence, which means there are some overhead. Cache coherence means each processor core can have its own copy of shared memory location. Okay? If one processor updates that location to some value, another processor has second copy, then this copy becomes obsolete data because the new data is created by the other processor. So this copy needs to be removed from this system, otherwise it will read the old data. Okay? So if you have multiple data in a cache in a different processor, then somehow the cache coherence hardware should maintain the coherence of these cache copies. Otherwise, other processor might see some stale copy of the data. Okay? These are called cache coherence. And the usual approach is they use write invalidation protocol, which means whenever some processor core is performing a write, then that address is visible on a shared address port outside of the chip or inside the chip sharing this processor core. So every processor core listens to this address line and this control line. If there is a write signal, then they catch this address because this address, if they have the copy, they have to delete it, otherwise they have old data. So by inspecting this write signal, if there is a write signal, they get the address, and using the address, they examine their cache. If they have, inside the cache, they have tag and data. Tag contains the address of each cache group. If their address matches, then it means that they have the old copy of their cache group. So it's invalidated. So this is called write invalidation protocol in general for cache coherence. So they may need to do this kind of communication that takes time and actually has overhead. So due to this overhead, the actual speed of is only less than half. The underflow speed is about 4.7. In real system, the actual speed of each is 10% serial fraction. Speed of each a little over 2.1, less than 2.2, right? Lower than half of 4.7, which the underflow set. Okay? So the actual speed of is actually lower because of their communication, work distribution, and cache coherence overhead. Okay? Any question?
Looking at that graph, it would seem that after having four processes, the gains are basically negligible, right? So why is it that we're moving towards 6 cores and 8 cores rather than just keep it at 4?
These are for PC, or this should be some spec integer application, which means ordinary application we are running on a PC or a server. But there are some applications that can benefit from multi-core, like database
for parallel programming,
application.
right? When you can have basically all the programs run on like by pieces on each core. That
If
each-
they are
each core doesn't
independent,
Yeah.
and if they have, they can be, most of them can be parallelized, then they can have a good speed up. So there are certain class of applications you can have good parallelism, and you can exploit parallelism on multi-core. But there are also some applications that may not be parallelized. It depends on application characteristics. Okay? Other questions? Okay, let's look at some other applications. These are database applications on multi-core. And amazingly, for these applications, for 64 processors, Oracle DSS 4 join is a DBA operation, two table join. So if you take database class, you know what is join, then they can get almost ideal speed up. Okay, and also DHDB2 decision support system scan and Oracle ADAG insurance, online transaction processing. These are all database related applications. They achieve very good speed up. So these over 50, some of them close to 63 or something like that. And what they can do is they have been trying to work hard to address this parallelization issue and try to exploit multi-core by reducing the serial fraction in hardware. So they try to reduce the overhead serial fraction within the hardware, operating system, middleware, and database application itself. So they try to optimize their application for multi-core in different levels of from hardware to operating system and up to application. And then they were able to achieve very good speed up for this particular class of application. Okay, and there are some applications also you can achieve some good speed up. These are examples. Lotus Domino's, Siebel CRM, these are some business applications. Lotus CRM is customer relationship management, business application. These applications have a small number of processes, but each process has many threads inside. Each thread is almost independent, and there are many threads, so you can run each thread on different cores, and you can have a good speed up. So if you have a small number of highly parallelized multi-threaded application, then you can have good speed up on multi-core. And even if you have single-threaded, which means no multi-threading, but many processes which are independent, then you can achieve good speed up. As long as you have many processes, then you can run each process on different cores. And examples are Oracle database and SAP applications. SAP is German business company. They specialize in ERP, enterprise resource planning, which is more larger set of business application, including this CRM. And this company application and Oracle database, they have many processes. Those are almost independent. DB, if you query application, they are almost independent. So you can run on different code and have good speed up. And Java application, as we have reviewed, Java is a single process, multi-threaded. Okay. And so Java language facilitates multi-threaded application, and Java virtual machine itself is a multi-threaded process. And this Java virtual machine provides scheduling and memory management for Java application. Since they have many threads, each thread can run on different cores, and they can have good speed up on multi-cores. And another way of achieving good parallelism on multi-core is if you have a same application, but you run multiple instances from the same application. This is multi-instance application. You can achieve good speed up by running multiple instances of the same application in parallel. Okay? So that's another example. So multi-core or multi-processor, if you have programs that most of them are serial, then you cannot have a good speed up. Okay? Because serial fraction, as Anders Flow states that serial fraction limits your parallelism. So most of your PC applications will not have much speed up or multi-core. But these applications, in addition to database workload, they have good speed up. And what they sometimes show is this: they can have good throughput instead of good speed up. Speed up is two-way. One is you run a single program and how much speed up you can achieve. This is different. You run multiple instances of the same program. Okay? That's same application, but different copy. You run on different core. Then you can have good speed up because each applications are independent, even though they are come from the same application. Then you can achieve good speed up. So some of the speed of measurement on multi-cores are showing this speed up. So there are two figures. One is actual speed up on single application, the other is some throughput speed up on multiple instances of the same application. And if you are more curious, I can give you more background on how can we measure and what are the speed ups. And performance are actually measured, and each speed up is measured by non-profit third-party organization called SPEC, Standard Performance Evaluation, something like that. If you go to www.spec.org, it shows all the performance figures for each processor, and also DB and transition processing and so on. And for spec figures, there are the spec integer, spec floating point. Spec integer is for PC application. Spec floating point is for server application. And there are spec weights for each throughput for multiple. So there are different figures for different type of machines and different type of application running. Okay? So nobody can argue because that's non-profit third-party organization. Because if you hear from this kind of performance numbers from Intel or AMD, another microprocessor company, then they always argue that their processors are better in terms of performance. But they show their application or their benchmark, their set of applications. So one processor, CPU might do better for their application benchmark, but for the other benchmark, AMD might be better. Because the applications are different. Okay? So you should not trust them. There are third-party organizations, they give correct numbers for standard benchmark. So all the companies that are involved in business participate in selecting benchmark sets. And it's changed from time to time. Right now we have SPEC 2006, which means these benchmarks are standardized in year 2006. And before it was 2000, SPEC 2000, before 1995, SPEC 95, SPEC 92, SPEC 89, and so on. Because the applications are changing from time to time. So they should work on a new set of benchmarks because since 2006, it's already 60 years from then. So they should work on a new set of benchmarks to reflect the application changes since year 2006. Okay? And also it depends on what kind of benchmark and what kind of application you are running. Actual numbers. But as I said, multi-cores, they are good at throughput, running multiple instances, but not single application, parallelization. They may not get good performance because of serial fraction. Okay? Any questions so far? Let's move to one specific example. So you should read all the examples that are in Microsoft Windows and Linux. Let's look at Solaris, which provides the most general framework for multi-threading. They provide user-level thread and kernel-level thread, and combined approach. Okay, so there are 4 thread-related objects in Solaris operating system. Solaris is Sun microsystem, Unix operating system is called Solaris. As I said, Sun is the leader in workstation and server market for the time being in maybe 1990s and up to early 2000 or mid 2000. Okay, when the workstation was used mostly, Sun invented Java, and in 1990s most of the graduate students actually used Sun workstation instead of PC. When I was a graduate student at University of Illinois, I was using Sun SPARC Station 10. I didn't use PC. At home I have a PC, Windows 3.11, but at my office I use Sun Workstation. And every graduate student and PhD students are using Sun Workstation because they have better power, better support for the simulation and other tools that students are using. So we bought many Sun Workstation from school. Okay. But as Sun actually now disappeared because it was acquired by Oracle. So Sun becomes an Oracle company. Sun disappeared means this workstation business is going out of business. If you look at workstation area, they are all going out of business. Sun Microsystem, HP gave up, and HP Workstation is using Intel's microprocessors nowadays. The IA64 and i10 processors, which I was involved in the design, that actually was co-designed by Intel and HP designers. And Digital Equipment Corporation disappeared. They are sold to Compaq, and Compaq also sold to HP, Hewlett Packard. And Hewlett Packard survived not because of the workstation, but because of printer and other business. Okay, and its ranking is going down and down because they are focused more on hardware. Okay, the only hardware company, top 10 IT company in the world is Samsung. Other than Samsung, most of them are Samsung and Cisco. Cisco might be still there, I'm not sure. So most of them are software companies. They are moving ahead. So right now, Apple, IBM, Microsoft, Google, something like that. Apple might be the biggest, and next might be IBM and Google, and then Microsoft. It's changing, but Microsoft will go down, I guess, and Apple will go down, I predict. But Google will go up, I guess. Google is the most powerful company, I believe. They are open source, and they have a big support group, including Samsung and other companies. And Apple is a closed platform, and I don't think it will sustain, because Apple used to use this closed platform before, and they didn't succeed. Okay, eventually, the smartphone business will be like PC business, and their margin will be lower and lower, and Apple will still problem in the future. Okay, Samsung will also have some problems because the margin will be lower and lower like PC. If you look at smartphones from other companies, they're about the same. Okay, I don't expect much from Apple's iPhone 5. This is Galaxy S3, but it's okay. Not much difference, and the difference will be smaller and smaller. Okay, that's the trend. Okay, anyhow, let's go back to Solaris. So Solaris has a process. The process is same as normal Unix process. So it has user's address space, memory image, and kernel stack, and user stack, and process control block. It has all the process related information in this process control block. It also supports user level thread implemented by user level thread library at the application level. So using this application library, you can create a thread user level. Okay, but these user level threads are mapped to Solaris library process. This is kernel thread actually. Each library process are mapping to one kernel thread. Okay, so library process can be used as a mapping between user level thread and kernel level thread. By default, they are mapped to one-to-one. User threads are mapped to a kernel library process, and library process is mapped to one kernel thread. Okay, and library process are kernel mapped to kernel thread. They can be scheduled by kernel independently. They may execute in parallel because thread is a kernel supports this multi-threading. Okay, so they can run on different cores or different processors. And they have also kernel threads that are not associated with write-A process. So that some of kernel threads are matched to write-A process, some of kernel threads are independent. The kernel threads are fundamental entities that can be scheduled and specified onto any processors by the kernel. And they use these kernel threads to implement their system functions. So they implement the Solaris kernel by kernel thread. Okay? Since they have kernel thread. If you do multi-threading on your kernel, then there are some advantages because since you support kernel thread, you don't have to do processor context switching. When you do thread switching, you can do kernel level, kernel thread switching, which means you don't require mode switch. Then kernel thread switching is lighter than process context switching. So you can implement kernel more efficiently than implementing using process. Okay? By supporting this kernel thread. So you can do all sorts of user level multi-threading and kernel level multi-threading. You can map user level threads to kernel level threads. Okay, in Solaris. So these are application level from out of process using user level application level thread library. You can create user thread. And each user thread you can map to write-A process, which is actually a kernel thread. So by mapping to write-A process, actually the kernel, right? Each write-A process they map to one kernel thread. And as I said, kernel itself, these system functions, kernels are implemented using multi-threading because they have separate kernel threads. Those are independently with this write-A process. So you can create threads by mapping to write-A process or calling to kernels, and kernels inside they have many kernel threads. Okay? So you can do all levels of thread or process related. You can create those objects. User thread, write-A process, and kernel thread, or process. In Solaris operating system. Okay, and these are traditional Unix, and these are Solaris. Traditional Unix supports only process, but modern Unix also supports multi-threading, including Linux. But this is old Unix. So in old Unix, they have this is process control block. They have memory image, process ID, user ID. Memory map is used to map execution files into private address space, which is memory image. So execution file, there are segments, text segments, data segments, and so on. Each are mapping to what virtual address. So if you have 32-bit virtual address, there are user space, each execution file, text segment started, the specific address, data segment started, some specific address, and so on. Okay, those mappings are maintained by this memory map. And again, there are some background materials I can provide that can explain further, but let's continue subject because we have lots of subjects to discuss this class. Okay. File descriptor, because they have file descriptor and they have IO tables and so on, page tables. Those are all process-related information. Page table is for virtual address space, private address space to physical memory mapping. File table, IO table is for resource management for files and IO device. And signal dispatch table is signals, as I said in the previous lecture, is a communication mechanism between two different processes. If you want to communicate, you can send a signal to another processor. A process cannot send the signal directly to another process. You have to go through the kernel. Kernel has to send the signal. And each process can react to each signal. There are several different signals. Signal block, signal break, all sorts of signals, signal kill, signal interrupt, and so on. There are several signals. And each signal you can define action. You can terminate. You can terminate and abort. You can terminate and dump. Dump means you dump your memory image onto your screen. Or you can also install user level handler. So for each signal you can do some specific application level. You can process on your own. Okay? Those are signal actions. And signal dispatch table defines these actions. What do you do? What do you do for each signal type? And here signal mask means what kind of signals are pending. Pending means it has been sent by another process, but it has not been delivered. And kernel should deliver the signal. And then the process can read the signal and can do the action. And in this mask, you can also disable or enable signal. So using the bin mask, you can disable, which means even if your signals are coming, you can disable, you can block. Okay? Only unblocked pending signals are delivered by the computer. That's called signal mask. Signal mask. And as I said, it will take maybe at least 1 hour to explain signal. Because using the signal, you can do all sorts of things. Some user level, this is another exceptional control flow. You can do exception, interrupt. Those are at the system level by calling the kernel, right? Exceptional, all this trap system code will go into the kernel mode, user into the kernel mode. But this is at the application level. You go through the kernel, but in application level, you can handle the signal. The signal can be used as an inter-process communication mechanism at the application level. But with the help of the operating system kernel. You have this?
No.
So in Solaris, instead of this process control block, they have separate, right? For each write-A process, they have thread control block. Okay? So they have write-A process ID, similar to usual this process ID, but this is thread ID, like kernel thread, thread priority, and signal mask. They can send the signal from thread to thread. So they have similar signal mask, similar to what process signal mask in this usual kernel level ID process. They have registers because each thread can be stopped and there can be context switching, and you have to save your registers. Okay? And kernel stack and user stack and so on. So there are more information you can read from your textbook that are managed by the thread control block. So since each process can create multiple threads, we maintain linked list structure and one thread control block for each thread. Okay? This is Solaris. And this is Solaris stage. There are 8 stages. So they are using some different terminology. So learn means ready. So we have reviewed process stage during the previous subject. There are ready and learning. And learn is mapping to ready. On processor is mapped to learning state. So this is actually CPU is dispatcher, and they are running on a CPU. They call it on processor. Okay, it corresponds to learning state in process that we have reviewed. This is ready state, ready to learn. There is a context switching, which means scheduled by the scheduler that they are learning. learning. And then if they sleep means it's blocked state, waiting for event. So these three states map to ready, learning, and blocked. Okay. So they are waiting for event. And if event occurs, they can wake up, they go back to ready state. And from learning state, they can be, the thread state can go back to ready state by preemption. Preemption happens by if there is a higher priority thread while your time slice runs out, then there is a preemption. Okay? And go back to ready state. And then if they become the head of the queue, they are dispatched. And context switching occurs and they are learning. Okay? Ready, learning, and blocked. Okay? This stop state corresponds to, this is for debugging purpose. So, for no debugging, you can call this stop function. Then they suspend it. They suspend it, it's not swept. They just pause. And the debugger can inspect. Okay? And then, from the debugger, if you continue, then you go back to ready state, which is long. The terminology is long in Solaris. Okay? Just the terminology is different, but this is mapped to ready state. And stop is used for debugging. So, debugging sometimes an exception, and Solaris is not an exception, it's just for going to stop state. Okay? And thread can terminate itself by calling exit system call. Exit is process, as you have discussed, by calling exit terminate. And they go to zombie state. And like zombie state, thread can go to zombie state. Zombie means they can do nothing. And to go, actually, they are still in the system. And to go to, but they are waiting for their parent to harvest. And this harvest is called leave. Remove T, this is a typo. The author didn't provide figures for instructors, so I don't have actual figures. This actually I modified a little bit to get correct. But your textbook actually have up-to-date figure. This should be a figure 4.15 from your textbook. You should look at the textbook that has the correct terminology. But these are some old figures provided by the author. So go to zombie state. And leaping means parents actually collect their child, and then child can disappear. And then you can go to free state. Free state means they have nothing, and they are waiting for operating system to remove from the OS thread data structure. If OS removes this free thread, then it's completely gone out of this system, and they disappear. Okay? Right, just people disappear, they are in a free state. They are waiting for OS kernel to remove. Okay? And idle state means doing nothing. You can create a thread by doing thread creation. And pinned is somewhat requires some explanation. Pin is, this is old slide. Don't I see. No. Actually, I sent you new slide around 2:57 and called Sam and asked him to notify you. So, did you hear from Sam or not? And this is yours. Oh, okay, this is updated. Sorry. Okay, this is updated. Sorry. Okay. So CPU, this is called CPU spinning, or called affinity scheduling. This was some research topic in 1990s when I was a graduate student. People are doing affinity scheduling to get some locality. So if you schedule your threads, if you move your threads from one core or one processor to the other processor, this is called process migration or thread migration. If you do that, then you have to start from again on a new processor then this, even if you run this thread, save the state and you have to restore the state, you will experience cache miss on a new processor core because cache will be, if content will be different, which will slow down your thread performance. Okay? So by pinning means it's like a pin. You pin this thread on particular processor or particular core. Right? Pin, you know what is pin? Okay? You pin your thread on the processor 1 or core 1. Do not move. Okay? If you don't do this, then the scheduling algorithm will stop and move to another processor or another core. And then when you run again, you access cache, and cache contents are different, and you experience cache miss, which will slow down your thread performance. If you pin, even if it cannot run, when this thread is resumed, you can run on the same processor. You have the cache, still has the cache coverage. You can access the cache instead of going to memory. So you can speed up this thread performance by pinning. It's called pinning or affinity scheduling. Okay? So pinning means you pin to particular processor or particular core. So they are suspended there. Okay? Pin. So pinned thread cannot move to another processor until it is unpinned. Unpinned means you can unpin, and then you can go back to run onto the same processor, and you can have good performance because they have some cache copies ready in the same processor. Okay? That's pinned state. Any question for Solaris?
What's the purpose of zombie state? Is
Jump.
there a difference between zombie states and free?
Zombie state means process can terminate, or in general, process can terminate by itself by calling action, but it doesn't go to go out. It still has some tables, some of the miscellaneous tables that it cannot declare. There are some system tables that are associated with process or thread. So to actually entirely remove the thread or process from the system, this parent process has to perform read function, which is like waiting for this process to terminate, and then the parent perform read function, which means repeat is like habit. You collect your process or thread, and then remove all these tables. But this is kernel thread. It's not completely remove the tables. There are still OS kernel data structure. There are some data structure you need to remove. So in a free state, they have to. They are still belong to the system in this Solaris library. So free state means they are awaiting from operating system so that they can remove from the OS data structure. So there are different levels from learning and calling the action. You cannot just add anything, but there are some system level information that need to be collected by this parent. After collection goes to the free state, and then the OS can remove the thread out of the system. Okay? But in general, this is for Solaris. In general, by leaping, it actually removes from the system in normal units. by just sleeping. You don't have to go to free state. This is Solaris specific state. Okay? So usually run by pulling the exit, jumping, by leaping, you disappear. That's the normal Unix process. There are some explanation about this page from the textbook, so you should read textbook, but pinning is not very explained in the textbook. I do some study from web and collect this information for your background information. Okay? So pinning is for this kind of performance schedule to improve the performance. Okay, by fixing the thread on a particular process code. Okay? And the other part you can understand from the textbook by reading the textbook. Okay, let's go to chapter 5. We have 2 chapters assigned for concurrency. The first chapter is mutual exclusion and synchronization. The second chapter is deadlock, starvation. We start from mutual exclusion. And the text explains these concepts. I think most of you, this is the first time you are looking at this terminology, right? So atomic operation, critical section, deadlock, live lock, mutual exclusion, race condition, starvation. How many of you have heard of these terminology before? How many of you? One? Only one?
I heard of deadlock.
Oh,
Yeah.
maybe 2. How about these Korean students? Is this your first time to hear this terminology?
I've heard of deadlock.
Deadlock, okay. How about atomic operation? Raise your hand. Only 2. Critical section. Oh, 1. Deadlock. Deadlock. Maybe about 10. Live lock. 1. Mutual exclusion. 2. Race condition. Nobody. Starvation. Race condition?
No.
Starvation.
Yeah.
Starvation too. Okay. And these are the explanation given by the author. Some of the definition, I believe this is incorrect. Okay. These definitions are fine, but a little not sufficient. So let me give you background. Each of these terminology. Let me give you what it does mean. Okay? You have to focus. Let's start from the atomic operation. The 2 of you have heard about atomic operation, right? Okay. So let's define what is atomic. Atomic means indivisible. Indivisible means it's do it at once. You cannot divide by half. One half done, half not done, that's impossible. Atomic means either do it all or do nothing. That's the atomic subject, atomic. Or it's also sometimes called uninterruptible. Excuse me?
I think there's a piece of literature that kind of reminds me of this.
Okay. So, atomic means it's like atom, you cannot divide bottom, right? Actually, atom you can divide, but atomic operation you cannot divide. Okay, it's indivisible. So atomic means it must be performed atomically, which means either success, do it all, or do nothing, failure, not in between. Okay? Success means you successfully do this operation atomically and update the machine state. Okay? You have succeeded in doing this atomically. Failure means you cannot do it atomically, then you cannot do nothing. You have no effect on the system state. You either do it all or do nothing. That's the atomicity. Okay? Atomic operation is defined by a function or action implemented as a single instruction some of the atomic operations are single instruction, or it can be implemented by a sequence of instruction or group of instructions that should be indivisible. Okay, indivisible. So atomic operation, sometimes they use a single instruction or they use a sequence of instruction, but both of them should be done atomically, indivisibly. Which means no other process can see an intermediate result. Atomicity means you fully update the state and then other processes can see the state. If you cannot fully update the state, then they give a failure and then do nothing. So process can see either success state or failure state, but not in between. Okay? That's the atomic operation. And there are two types of single instruction or a sequence of instruction, but they should be indivisible. And this atomic operation can be implemented by hardware or by software. Okay. And hardware level atomic operation, these are hardware machine instruction. Machine instruction. Test and set is you look at some memory location and you test some value. If some value is same as test value, you set. If not, then you cannot set. And this is provided by most processor CPU as a single atomic instruction. And compare and swap or compare and exchange is another machine instructions. And sometimes some processors support fetch and add, and some processors support load link and store conditional instruction and so on. These are all machine level instructions that are performed atomically because they are going into some memory location and test some value and exchange. And memory location is shared location, there is only one location. So if one processor is accessing the location, no other process or thread can access the location, only one by one. Okay, so that should be done atomically. And the machine usually supports these instructions. And this instruction, using this instruction, they can implement some software solutions efficiently. They have some advantage and disadvantage of using these instructions. We will discuss further. But anyhow, atomic operations can be supported by hardware by using this machine instruction. Or you can use software solutions. There are some various solutions, but usually they run a group or sequence of instruction in a critical section. You don't know what is critical section, I'll explain. Okay? So there are some atomic operations, and atomicity is generally enforced by mutual exclusion. Mutual exclusion means like exclusive OR. Only one process or one thread should work on some shared data structure or a piece of code. It's called critical section. And nobody can interrupt during this critical section to guarantee isolation from other concurrent process. So atomicity requires some mutual exclusion. What is mutual exclusion? Mutual exclusion is the problem of ensuring that only one process or thread must be in a critical section at a time. So there are a section of code called critical section. And to support mutual exclusion, only one process, so critical section, maybe entry and critical section SC. There are a sequence of instructions, or it is implemented as a program language, a sequence of statements. The machine level, there are a sequence of instructions. If they define as critical section, mutual exclusion means only a single process or thread must be in this critical section. Only one, not two. They have to enforce this to provide atomicity. Critical section is defined as a piece of code that has an access to a shared resource or shared variable. That's called critical section, usually shared resource. If you don't support enforce mutual exclusion, then you cannot implement this atomicity. To enforce atomicity, you have to enforce mutual exclusion, which means critical section you have to enforce only one process or thread should be inside this critical section. So atomicity definition involves some mutual exclusion. Mutual exclusion requires in a critical section, only one should be in the critical section. So how do you support mutual exclusion? You can do it at hardware level. For mutual exclusion, the easiest way is using this disabling interrupt. Then you can support mutual exclusion. If you support mutual exclusion, you can support atomicity. Disabling interrupt should be supported by hardware. So when we discuss interrupt, right? Talk about interrupt enable or interrupt disable. Right? You can enable or you can disable interrupt by using an instruction. Okay? Some hardware support this kind of interrupt enable or disable. Okay? So with this kind of hardware support, disabling interrupt is usually provided in the form of OS kernel primitive. So you can, before you go into critical section, you disable interrupt, and then after you perform critical section, you can enable interrupt. Disabling interrupt when you perform or execute this code, critical section code, you do not allow context switching because you disable all these interrupts. Okay? So no context switching means no other process or thread can be interleaved with this process or thread because you disable interrupt. So when they execute critical section, you're on your own. Nobody can interrupt them. CPU OS cannot schedule any other thread or process when this process is doing this code. Okay, because you disable your interrupt. So because there is no context switching, you guarantee mutual exclusion. So this can be performed automatically by a single thread or a single process. Disadvantage, this works for only uniprocessor. Okay. Multiprocessor, if you have multiprocessor, in other CPU there can be interrupt. And it can be let me think about it a little bit. So it can degrade performance because there is no multi-programming or multitasking. The issue is if you have multi-core or multi-processor, there can be interrupt. And what happened to this critical section?
Multiprocessor can be executed multi-process. So one other processor using this critical section at the same time without interrupt.
That's right. That's a good point. So if all the critical section, the meaning is they have some shared resource. If there is another processor core with the same critical section, same resource, for uniprocessor you can avoid this context switching. But multiprocessor, multi-core, separate thread with the same resource, same critical section, associated same resource, then there can be an interrupt. Okay? Then this code can be interlinked with another, the same shared resource with the different thread. Then it can have problems. Okay? The critical section is usually associated with resource. That's the resource R. Okay? Critical section with this resource R. Uniprocessor is okay, but another processor can use the same critical section with this resource R. Enter, exit. And processor 2, processor 1. You cannot avoid interrupt on a different processor because this disable interrupt, this is effective only for your processor, not for other processors. And this code can be interlinked because they are associating with the same resource, and then it can cause problem. If it's different resource, that is okay, but same resource, with different, same type of resource, and critical section, then when he tries to enter the critical section, we cannot prevent another thread or process going into that critical section associated with the same resource, because other thread can also use the same resource. In multiprocessor, each thread can be scheduled to different processor core. Okay? And each processor core can use the same critical section associated with the same resource. Okay? But for uniprocessor, the only way to go into the resource conflict is for this code. But in multiprocessor, other application, but that application might have access to the same resource. They use the same critical section associated with the same resource. Then it can create a problem. That's the situation. Let me look at the textbook. Page 230, it explains about interrupt disabling. This says is another problem is that this approach will not work in a multiprocessor architecture. And the computer includes more than one processor. It is possible for more than one process to be executing at a time. In this case, disabled interrupt do not guarantee mutual exclusion. That's the only explanation. So it doesn't have much explanation, but okay. The situation is multiple threads or multiple process might compete for the same resource. Okay? If you have a single processor, by disabling interrupt, you can provide mutual exclusion. If you have multi-processors, another thread might access the same resource. They have to use the same type of critical section associated with the same resource. Okay? If you disable interrupt on this particular processor core, it affects only this processor, but not the other processor. So the other processor goes into this critical section, and then because it's associated with the same resource, then you have conflict. Even though they are different critical sections, actually they are associated with the same resource, then that creates a problem. So this is only for uniprocessor, not for multiprocessor. And this can be used for multiprocessors, but this is usually supplementary hardware support. Using this hardware, you can support software calls. You can implement using only this, using busy waiting. That has advantage and disadvantage. But it's usually used to implement the software such as lock and semaphore. Okay?